Okay, so 1.6 continuity. So what is, first of all, what's the continuous function, right? If you can draw a graph without lifting your pencil, means it's a continuous graph. So for example, when you have a parabola, okay, so you can sketch a parabola without lifting your pencil. So it means that this parabola is continuous at all times. But some functions will be continuous for some domain and not continuous at some points. For example, you may have a rational function. So let's say there's an asymptote here, right? So you sketch this part, you have to lift your pencil to sketch the second part. Means this function is discontinuous at x equals 0. So conditions for continuity at x equals a. So there are three conditions. One, if f of a exists. Two, limit of f of x as x approaches a exists. Number three, if f of a is equal to the limit of f of x as x approaches a. So if these two are equal, then we can say that the function is continuous at x equals a. All polynomial functions are continuous for all real numbers. We already talked about this before. A rational function, let's say we have h of x equals f of x over g of x, is continuous at x equals a if g of a is not equal to 0. Means when you substitute a in here, if you don't get 0 for the denominator, means this rational function is continuous at x equals a. So now we're going to do some analysis to check the continuity with an example. We have example 1. Analyze the continuity of the following functions at x equals 4 and illustrated by, well, actually this is number 1 is already has a graph, so you can scratch that part. Okay, so we're going to analyze the continuity at x equals 4. So number 1, right, condition, we check if f of a exists. So we are going to check if f of 4 exists. So when we look at a, so when x equals 4, we see a hole. So f of 4 actually does not exist. Okay, so it fails the first condition. If something fails, the first condition, then you don't have to go ahead and then check other conditions here. If it fails the first one, yes, this function is discontinuous at x equals 4. We can directly say it. Okay, you don't have to check the other conditions. So now we can say f of x is discontinuous at x equals 4. It failed the first one directly. Let's look at b. We have this function now. So again, we are going to do analysis starting from number 1. So we are going to check if f of 4 exists. F of 4, when x is equal to 4, y equals 6. So it passes the first condition. Now we're going to check the second condition, which is the limit. We're going to check the limit of f of x as x approaches 4. Okay. So now this piecewise function, we're going to check left side limit and right side limit. So left side limit, as you see, is 3. Right side limit, as you see, is 6. So left side limit is 3, right side limit is 6. So limit of f of x as x approaches 4 does not exist because left side limit is not equal to right side limit. So now this b, part b, this function fails the second condition. Okay, so then we don't need to go and check the third condition. It failed the second one. We say then f of x is discontinuous at x equals 4. Now let's look at C. Again, we start from number 1. We're going to check f of 4. F of 4 exists, that is equal to 2. It passed the first condition. Let's check the second condition. We're going to check the limit of f of x as x approaches 4. So limit from left is 4. Limit from right is 4. So we have a limit. Left side limit equals the right side limit. So limit of f of x is 4 in this case. Then we can check now the third condition. So we're going to check if f of 4 equals to the limit of f of x as x approaches 4. Okay. So f of 4 is 2, limit is 4, they are not equal, so it failed the third condition. So we say f of x is discontinuous at x equals 4. Yeah, we check here left side and right side limit because see it is broken as you say. So there are two pieces here. So therefore I show the left side limit and right side limit. But actually now you can directly see that limit does not exist. You know, without even doing this, you can see that that limit does not exist. Directly. Okay, now we're gonna do D. We have f of x equals x cubed minus 2x squared. Yes, if it is not asked specifically to calculate left side limit or right side limit, and if you see that it doesn't exist, you can say it doesn't exist. So we have x cubed minus 2x squared. So we're going to do the analysis for this. Again, for x equals 4. Okay. So condition 1, we check if f of 4 exists. So this is a polynomial. We can just use substitution method here. So 4 cubed minus 2 times 4 squared. So that is 64. 16 times 2 is 32. So that gives you 32. So now check the second condition. Check the limit. Again, yeah, so this is just getting the value, but this is limit. But again, this is a polynomial function. You can just sub the value to get the limit. So that is also 32. So now you check the number 3. You check if f of 4 equals limit of f of x as x approaches 4. So we see that both of them are 32. So therefore, this one passes the third condition. So they are equal. Since it passed all three conditions, then we say that f of x is continuous at x equals 4. And actually, if you were to sketch this, okay, so you could factor x squared that gives you x minus 2 here. And if you sketch, zeros are 0 and 2. It's a cubic function with a positive leading coefficient. It goes from quadrant 3 to quadrant 1. So there is a order 2 at x equals 0. It is going to bounce off at 0, pass through 2. Pass through 2. Okay, and then as you see, if we look at 4, okay, so that value is 32. The function is continuous at x equals 4. E, condition 1. So we're going to check f of 4. So this is a piecewise function. Check where 4 is included. So 4 is not included here, but here, right? X greater than or equal to 4. So that answer is 6 then. So 2, we're going to check the limit as x approaches 4. Okay, so this is a piecewise function, and as you see, the break point is 4. Therefore, you have to check left side limit and right side limit. Left side limit, so we'll look at this one, right? So you look at the number where x is like 3.9999. It is not 4, but it is closer to 4 from the left side. So you use this equation here. So 5 minus 4 gives you 1. So right side limit, we'll look at this one, right? Because so you look at x value that is 4.0001, not exactly 4, but that. So you use the second equation, which is 6. So left side limit is not equal to right side limit. So it doesn't exist. So it failed the second condition. Therefore, you don't need to go and check the third condition. We can say now that f of x is discontinuous at x equals 4. If you were to sketch this function, okay, so let's say this is 4. So when x is greater than or equal to 4, y equals 6 line. And when x is less than 4, it is 5 minus x. So y-intercept is 5. And slope is negative 1. Y-intercept is 5. Slope is negative. Okay. So, and when x is 4, 5 minus 4 gives you 1. This is 1. And there is a hole here. Okay. So, and when you look at this, you can directly see that the function is discontinuous at x equals 4. Next example. What value of constant c is the function continuous at any number? Okay. So if they are continuous, so this is a piecewise function as you see. Okay. So if those pieces are somewhat connected, then the function is continuous. Let's say you have a line, okay, and parabola, 2 pieces. If these 2 pieces are attached, then the function is continuous here. Let's say that is x equals 3 for this case. Okay, but if those two pieces are not attached, that is the second condition, at x equals 3, then we say that this function is discontinuous at x equals 3. Okay, so there two things are here, right? So we have a line, we have a parabola. So we want this function to be like this. So we want those two pieces to be attached together. Then how can we do that, right? So we can only have this if this piece line and that piece parabola have the same y value at x equals 3. If they don't have the same value when x is equal to 3, then it is discontinuous. So we're going to use this information here. Okay, there's only a single y value when x is equal to 3 for line, for the parabola, so that they are attached. So this means when I substitute 3 in the first equation and second equation, I should be getting the same y value. Okay, so substitute 3 here. So 3 plus c. Substitute 3 for x here. So you get 9c plus 1. Okay, so that gives you 2 equals 8c. And looks like c is 1 over 4. So when c is 1 over 4, okay, so now that is the equations. Then you get the same y value, means that these two pieces are attached. When you substitute 3, let's say here, so you get 13 over 4. Substitute 3 there, 9 over 4 plus 1, also 13 over 4. So they have the same value. If c was something else, let's make it up. If it was, let's say, x, c is making it up 4. Okay, let's say it was 4. Then for x squared plus 1, right? Then when you substitute 3, what do you get? 7. 9 times 4 is 36, 37. See, they don't have the same y values. Means this function would be discontinuous at x equals 3. Okay? The answer is 1 over 4.